Good morning, grade 10s. Welcome to our first lesson of exponents. It's Thursday, and today's introduction is just going to be a revision of all the exponent laws that you learned in grade 8 and grade 9, plus a few more difficult ones, just so you can get your brain thinking for a grade 10 level. So this would be the page that you received on Instagram. You also then would have received something like this, revision of basic concepts, and then more challenging examples. I am now going to ask you to open your book and write today's date. We're just going to look over the exponent laws very quickly. So today's date is the 9th of the 4th, 2020, and we are doing exponents. Okay, I'm going to be playing around with the settings sometime, so I'm just going to check better with the lights on or better with the lights off. Do I need to make it a bit brighter now? Okay, that's where I'm going to stay with the setting for now. Okay, exponents. So the first thing you need to know about exponents is an exponent looks like this. It has a base, it has an exponent, and together it's called a power. So that's a base. This is an exponent. And then together it's called a power. I often, and it's lack of concentration on my part, swap these two around. So often I call this a power, but this is an idea. When we have a number that looks like this, a base with an exponent, we call it a power. It has certain laws that go with it, okay? And the first law looks like this. It's the law of when I'm multiplying powers, okay? What must happen is when I'm multiplying powers with the same base, okay, you keep the base and you add the exponents, okay? So I would say m plus n. It is not a to the power of mn. That would imply that I multiplied the exponents. I didn't. I must add the powers. That is my first rule. And an example would look like this. A cubed times a squared. Like bases, keep the base, add the powers, a5. The part where children get confused is when I have, for example, 3 cubed times 3 squared. And then the children tell me, okay, 3 times 3 is 9 to the power of 5. And this is wrong. This is not the right answer. The same law applies. What happened? You had the same base, so you kept the base. So I have the same base, so I keep the base, and I raise that to a power of 5. This is the right answer. So that's one common mistake that happens with that law. The second law is when I divide like bases. So I have a to the power of m divided by a to the power of n. Same base, so you keep the base and you subtract the exponents, m minus n. It can also look like this, remember? That's also division, and you would say a to the power of m minus n. Please remember that if m and n, so let's have a proper example very quickly. So if it looked like this, a to the power of 10 over a to the power of 3. If it was linear, it would look like this, a to the power of 10 and a to the power of 3. But what will we do? 10 minus 3 gives me a to the power of 7. This step is frivolous. You don't have to put it in. This would be your final answer. But remember when it looked like this, perhaps I had a to the power of 3 on top and I divided that by a to the power of 10. I'm still dividing, so I still have to subtract, but where does my division happen? My division happens at the bottom. You always move the smaller to the bigger, and that's where my subtraction happens. So in the denominator, I have a to the power of 7. What stands in my numerator? A 1, because this moved down. Not a 0, but a 1. And this also happens with negative exponents, which you learned last year, the division. So keeping in mind that if I have a negative power, a to the power of negative 1, I never want these negative exponents, sorry, not powers, I never want a negative exponent. What do? I take it to the bottom. Remember, this stands on the imaginary 1, and I would take this to the bottom, and my answer would be a to the positive 1 in the denominator and an imaginary 1 on top. So, for example, if I had 2 to the power of a negative 3, my problem is this power here. It's got a negative exponent. It stands an imaginary 1. I take it to the bottom, and I end up with 2 stays at the top, because 2 is not a power. Do you see it doesn't have a base and an exponent? It's just an integer. So I can't apply exponent laws to 2 because it's an integer. So 2 stays at the top and a cubed moves to the bottom. This is familiar to you. You should remember it from grade 9. And it works in reverse as well. So say, for example, if I had 1 over 2a to the negative 3, I don't want this negative power because it's got a negative exponent. So I move it to the top. The 2 doesn't go anywhere because it's an integer. So I get a to the power of 3 on top over 2 at the bottom. Okay. That's a little bit of negative exponent. So say, for example, if I had x negative 3 y 4 over x 4 y negative 3, I'm dividing, so I still need to subtract. Do you remember how this works? You move the smaller to the bigger. So I move this negative 3 down because negative 3 is smaller than 4. And when I subtract, a negative, take away a negative becomes a positive 3. You bring it down and it disappears. And what happens to the y? You take the smaller to the bigger. And when I subtract negative 3, a negative and a negative make a positive. And that moved up to the top. And my answer for this would be y7 over x7. Now, just because they share the same exponents doesn't mean that they are alike in any way. I can't move the one to the other. They don't cancel. This would be my final answer. So that's a little bit of negative exponents that you should remember. Okay. The other law we have is when I have a power raised to an exponent, or a power to a power. This is also why I get confused with my terminology, because we have funny little sayings. So an exponent raised to a power. Anyway, what do? We have to bomb the exponent in. And when we bomb, and it's an explosion. This is where I times. So what do? Keep the base, multiply the powers. M times n is mn. M times m is mn. And an example of this could be x to the power of 2 raised to the power of 3. I bomb it in. Powers go to powers. It's an explosion. I times x to the power of 6. Okay. Another mistake is, for example, if I had this, 3 to the power of 2 cubed. Some kids want to say 3 times 3. They take it there and they take it there for some reason. And then they tell me my answer is 9/6 or something. That is wrong, okay? Powers only distribute to powers. So this little exponent must go to the exponent, not to the base. And that's where my multiplication happens. So this stays. Keep the base, just like you did here. You kept the base, you multiplied the powers. You kept the base, you multiplied the powers. So you keep the base and you multiply the powers. Okay? Then my other rule comes in is when I've got a monomial. So I've got AB raised to the power of m. Okay? This m must distribute to both of these. Now remember, exponents go to exponents, or powers go to powers. This b has an imaginary power of 1, and this a has an imaginary power of 1. So when I bomb it in, I keep the base of a, and I say 1 times m, which is m. Keep the base of b, and I say 1 times m, which is m. Powers always go to powers. How would this look like if I had a real example? If I had x squared y cubed to the power of 3, okay, it must bomb to the x and to the y. So, base of x, 2 times 3 is 6. Base of y, 3 times 3 is 9. Okay? This also works, but remember, this is only a monomial. It does not work if I had, for example, x squared plus y cubed to the power of 3. I'm not allowed to bomb this in, okay, because I don't have a monomial inside. What should I be doing with something like this? Something like this, I should be opening up FOIL brackets. And it would have 3 brackets because I had a power of 3, not just 2 brackets. So it doesn't work with that, only monomials. Where do kids get confused? Well, if I tell them 2x squared y cubed raised to the power 3. Remember, this 2 also has an imaginary 1 over here. So you have to take the 3 to all 3 of these bases, okay? It has an imaginary power of 1. You don't say 2 times 3, which is 6. You take the power to the power, and I end up with 2 to the power of 3, because 1 times 3 is 3. X to the power of 6, y to the power of 9. Please don't forget that. If I had, for example, inside my brackets, I had integers or like terms. So if I had 2 times 3 raised to the power of 2, okay, I can either distribute in and get 2 squared times 3 squared, okay. Why? Because what does this give me? This gives me 4 times 9, and 4 times 9 is 36, okay. Or what can I say? Because they are like terms, I can multiply these integers. I can say 2 times 3, which is 6. So that gives me 6 squared. And what is 6 squared? Also 36. These work out the same. Okay. And if I had to give you something like this, 2 times 3. I see this is on your worksheet, to the power of x. You could say 6 to the power of x, or you could say 2 to the power of x times 3 to the power of x. This is quite interesting because 6 to the power of x, these two things represent the same thing if you think of the example we looked at just prior to this. So perhaps keep this in mind. Okay, cool. Then we have the law or the rule where anything raised to the power of 0 is 1, and it's important to establish what the 0 belongs to. So if I gave you 2x to the power of 0, the 0 only belongs to the x. So that means I still have the 2, it doesn't change, and this means times. So I've got 2 times 1, which is simply 2. But if I gave you this, the 0 belongs to the whole thing. So the whole thing automatically becomes 1. Okay, so that's the power raising to the power of 0. When we are square rooting, and we did speak about this a little bit when we factorized, but remember when I'm square rooting, okay, my answer to square rooting a variable, now this is confusing if you look at the law. This is an imaginary power of 1, right? The answer to this is A, keep the base and divide the power by the root value. So 1 over n. So how would this look like in real life? If I had the square root of x to the power of 16, okay, you keep the base and you divide the power by the value of the root. So x to the power of 8. Or if I had the cube root of x to the power of 12, keep the base, divide the power by the value of the root. So I get x to the power of 4. Okay. Always remembering, and I'm just going to do one of these, that if I had the square root of 16x 16, you still square root this integer. That its laws doesn't change. It's still an integer. It's not a power. Okay, so I get 4. X to the power of, you divide that by the value of the root, and I get x to the power of 8. Okay, very quickly, I'm sure you can understand this, that if I had a fraction, a over b to the power of n, that n belongs to both the numerator and the denominator, so I get a to the power of n over b to the power of n. But the interesting thing I want to look at with you very quickly is if I had a over b in a fraction to the power of negative n. And some of us didn't show you in grade 9 because it wasn't very necessary, and there are ways and means around it. It's just a shortcut, I suppose. But when I have a fraction raised to a negative exponent, how do I make that exponent positive? I can simply switch the fraction. Okay, how does this work? Because if I distributed this in here and I had a to the negative n over b to the negative n, I don't want these negative exponents, so I swap them. I take that to the top to make that one positive, and I take that one to the bottom to make that one positive, and I'm left with bn over an. But on this side, If I've swapped it already, what can I do? Distribute it straight in there, bn over an. And those two things are the same answer. So it's not a law that you have to know, but it does make your life easier. Okay. So just remember though, if I had something like this, x to the negative 2 over y to the negative 3 raised to the negative 3, for example. I want to make this positive first. How do I make it positive? I swap these two things around, okay, to make this positive. Now, when I'm swapping these two things around, okay, the swap influences this first and foremost. So I'm swapping, but I haven't changed the negativity inside here, because all I've changed by swapping is this negative, okay? So in order to make then these positive, they'd have to do their own swap again, if this makes any sense. So then I would have to, well, hopefully it does make sense. So then I would have to take this to the top and this to the bottom again to create this being positive, and the cube stays on the outside, which you would then distribute in. And I end up with x 6 over y 9. And how does this work? Because if I had to distribute this straight in here, I would have gotten y to the negative 9 over x to the negative 6, and this is still a problem because I still have negatives. So it would still mean me taking that to the top and taking that to the bottom, and what do you think I'd end up with? Positive 6 at the top, positive 9 at the bottom. So this is quite a complicated law that I know a lot of you did struggle with in grade 9. But it's time to face our fears, and that's what we're going to do today. So that's the end of your exponent explanation. Please make use of textbooks and other resources if you don't understand that. Okay, I'm going to move on to these worked examples over here. This must have a line underneath it. This is p to the negative 2 divided by t to the negative 3. So I'm just going to zoom in very quickly so you can see what I'm doing. Those are the questions that I'm going to be doing. And I'm going to zoom out. Revision of basic concepts. That can be your next little subheading. And we're starting. Because it's a revision, I am going to go quite fast. Number 1 says p over 2 squared times p to the negative 2 over t to the negative 3 squared. Cool. Easy peasy. Going to bomb this into powers. So this must go to that power and that must go to that power. And here I'm going to sort out the negativity first. So I'm just simply going to take that to the bottom. I'm going to take that to the top. Remember, this affects this negativity now because this is a negative. So I end up with p squared over 2 squared times t cubed over p squared all raised to a 2. This I can now bomb in here, and I'm left with p squared over 4, I'm changing it, times t6 over p4. Cool. Now it's fractions, and we learned a lot about fractions yesterday on your Wednesday video. Times top with top and bottom with bottom. You can cross cancel. I'm going to leave that because we've got variables, but you could do it already. So I get p squared t6 over 4p4. What do I notice? Like bases. So I can simply move the smaller base to the bigger base. So this is a smaller exponent, so this drops down, becomes negative 2. And my final answer is t6 over 4p to the power of 2. And that's my final answer there. Okay, question 2. Looks like this. 27 to the power of x times 1 over 27 to the power of x. Okay, I can already see I'm going to have like bases, so I'm going to need to relate them somehow to each other. Okay, I'm going to keep this as 27x times. If you had to bomb this x in first and foremost, you could. Just remember that 1 to the power of x is 1. Why is that? Because if I replace x with anything, I'll always get 1 out. Because 1 to the power of 100 is 1. 1 to the power of negative 2 is also 1. So it doesn't matter what that x is if you decide to bomb it in first. If you have 1 to the power of x, it stays as 1. What I'm going to do is, because we must be thinking cleverly, is I'm going to take this 27 to the top rather. And I'm going to have 27 to the power of negative 1 raised to the power of x. Remember, it has a positive 1, so when I take it to the top, it becomes negative. Why do I do this? Because it gets rid of that confusion of 1 to the power of x thing. If I bomb this in there, I end up with 27x times 27 to the power of negative x. Okay, cool. Like bases, what are my rules? Keep the base, add the powers. So I have x plus negative x, which is simply x minus x. Remember, x plus negative x, that just becomes a negative. And x minus x is 0, so I end up with 27 to the power of 0, which is simply 1, because that 0 belongs to the whole thing. It's 27. It's not 2 times 7. Okay. Cool. Question number 3. You have the cube root of x to the power of 36, y negative 21. And we know what we do. With our powers, we divide them, the exponents, by the value of the square root or the cube root. And I got x to the power of 12, y to the power of negative 7. Here's my problem. I don't want these negative powers, so I take it to the bottom. Remember, this stands an imaginary 1. What do I mean I take it to the bottom? I mean in my denominator, I now have y to the positive 7, and my numerator doesn't change because it wasn't the problem. That was question 3. Question 4, 2 to the power of m plus n over 2 to the power of m. Now, this is quite a cool concept, and these concepts we're going to draw on in grade 10. If I've got 2 to the power of m plus n, this was an exponent law. What do exponent laws say when we add powers? We have been multiplying like bases. So if I have this base of 2, it means I've been multiplying like bases. And what did each exponent did these have? This had an m and this had an n. Because when I'm multiplying like bases, you keep the base and you add the powers. This is law 1, just in reverse. So I'm going to rewrite this as 2 to the power of m times 2 to the power of n, all over 2 to the power of m. And what do you see? Monomial over a monomial. What am I allowed to do when I have monomials over monomials? I'm allowed to cancel off things that look exactly the same. Those two things look exactly the same. My answer is 2 to the power of n. Okay. Question 5. I have xy squared raised to the power of 3 over x squared y cubed raised to the power of 2. So I take this in, taking powers to powers, and when I'm bombing in, it's an explosion, so I must be multiplying. And I end up with x cubed y6 over x4 y6. Monomial over monomial, I can cancel things that look exactly the same. And what do I do with this x cubed and the x4? I move the smaller to the bigger. The cubed is smaller, so I move it down, and my subtraction happens there because I'm dividing. That cancels. So in my denominator, I have x to the power of 1. You obviously don't have to put that 1 in. What's at the top? A 1, not a 0, please. This is all grade 9 stuff. Okay, so now I've got 2x to the power of 0 plus 2x to the power of 0. Who does this 0 belong to? Only the x, and to this whole thing. So here, the x becomes a 1, and over here this whole thing becomes a 1. 2 times 1 is 2, and 2 plus 1 is 3 would be my answer. Okay. Number 7, I've got 2 to the power of negative 2 plus 2. I want to change this around. Do this without your calculator, please. I don't want this negative power. I take it to the bottom. So in my denominator, when I take it down, the 2 doesn't change. The base doesn't change signs. Only the exponent changes signs. So I take it to the bottom, and I get positive 2. And there's a 1 at the top plus 2. Okay. This becomes 1 over 4. So a quarter plus 2, I'm changing this immediately into a fraction with the same denominator. 8 over 4, because 8 divided by 4 is 2. And what do I have? 9 over 4 is my answer. Okay. And then lastly, I've got 2 over 3 raised to the power of a times 3 over 2 raised to the power of negative a times 3 over 2 raised to the power of 0. Okay, cool. So this power of 0 belongs to the whole bracket. So that thing's going to become 1. My other problem is I don't want this negative on the outside of a bracket. So what do? I swap the inside of the bracket to change this negative. When I'm changing the negative on the outside, it doesn't change the powers on the inside. So I've got 2 over 3a times 2 over 3a, swap these two, that became positive, times 1. What do I notice? I don't even have to bomb this a in. This and this are the same. My bases are the same and I'm multiplying. So what do? You keep the base and you add the powers, a plus a. And remember, a plus a is not a squared. A plus a is 2a. Okay, cool. This is also quite an important concept. And you'll see why a little bit later, that the a plus a becomes 2a. Or 2a is written as a plus a, not as 2 times a. Okay, so 2a can be written as a plus a, not only as 2 times a. And that was my revision of basic concepts. You then have this exercise given to you, and you're going to do most of it. We'll put up probably exactly what you have to do. Then I just want to move over to more challenging examples very quickly. And I want you to try these on your own because these are the important ones. I'm just going to discuss them with you very quickly, each of them. So for example, with 1, and if you want to see it without me discussing, pause now and try it on your own. But for 1, I've got a over b x plus y times b over a x minus y. And just before this, we saw, how do we work? This is law 1 of exponents. If I'm adding, that means I must have multiplied like bases. Okay? So how can I rewrite this? Okay, so how can I rewrite this? I'm reversing law 1. So they had the same base, and I was multiplying them. That way, I kept the base and I added the powers. So I'm going to do the same here, even though this is negative, which assumes that we divided. But it would also mean that I had b over a to the power of x times b over a to the power of negative y. Okay, so I'm going to move these together right now because they've got powers of x's. So I had a over b to the power of x times b over a to the power of x. And then I'm going to look at these y's. I've got a over b to the power of y that I got from there. What do I do with this negative power to make it positive? I switch the inside of the fraction. So here I have a over b to the power of y. Okay, this is easy, this section here, because I've got the same base. So you keep the base, you add the powers. I'm just going to focus on this. Earlier in the beginning of this video, we saw that 2 times 3 to the power of x gave me 2x times 3x, and you can go back and look. But 6 to the power of x is the same thing as these two things. So if I multiply, if I have the same exponents and I multiply the bases, that's a law I can actually do. Okay, so drawing on this knowledge, they have the same exponents. I can simply multiply the bases. So what does this become? If I multiply the bases, I get ab over ba all raised to the power of x. This is this knowledge that we saw in the beginning. Okay, times on this side, I've got a over b to the power of y plus y, which is 2y. Y plus y, which is 2y. Okay. All of a sudden, what do I see here? Okay. I'm just going to erase this board quickly. I'm going to write it over here. I've got a times b over b times a to the power of x times a over b to the power of 2y. Okay. What do I see over here? Monomial over monomial, which means I can cancel things that look exactly the same. That cancels, okay? And my b's cancel. And all of a sudden, I actually have 1 to the power of x times a over b 2y. This is an a. And what did we discuss earlier about 1 raised to an x? It always comes out as 1 times a over b to the power of 2y. So my answer is simply a over b to the power of 2y. That's a very complicated one. So what you should do is, after watching me do this, you should pause and go see if you get the same answer. Let me just very quickly re-explain that 1 to the power of x means if I raise 1 to anything is 100, 1 to negative 100 is also 1. So it doesn't matter what x is, my result is always 1. That would be the first one. Under more challenging examples, question 2, a to the negative 1 plus b to the negative 1 raised to this negative 1. Why can I not distribute this negative 1 in? Because I don't have a monomial. So what do? I'm supposed to change this right now. So let's change these individually. Take them both to the bottom. I get 1 over a plus 1 over b raised to a negative 1. Okay, I have fractions, and what did we learn about when we're adding fractions? Sorry, let it focus. We have to have the same denominators. What denominators am I going to have here? I'm going to have AB, and I'm going to have AB, because I can multiply each of these. I can multiply this by B, and I can multiply this by A. So I'm left with B plus A. So my answer is A plus B over AB raised to the power of negative 1. And I still don't want this negative. So how do I get rid of a negative on the outside of a fraction? I flip the fraction. And my final answer is AB over A plus B. And this becomes the positive one then, which you don't have to write. I cannot go and cross-cancel these things. Why not? Because I have a monomial over a polynomial, and there's no way I can factorize this polynomial at this point. So there's no point on cancelling. That's my final answer. Okay, question 3, again without your calculator. 3 squared over 3 to the negative 2 minus 6 to the negative 1. What do? We have 3 squared at the top. At the bottom, I'm actually just going to write this linearly so that I don't run out of space. So I'm dividing by 3 negative 2 minus 6 negative 1. Okay. So at the bottom, I want to get rid of these negative exponents. So I take that to the bottom. And I have 1 over 3 to the power of 2 would be 9 minus 1 over 6. When I'm subtracting fractions, what happens? I need the same denominator. What denominator am I going to choose? What goes into 6 and 9? 9, 18, 27, 36. 36. Because I can times this by 4. And I can times this by 6. And I end up with 4 minus 6 over 36, which is simply 9 divided by negative 2 over 36. And this is simple. You can cancel. This becomes, I can tip in times first, but this is 1 over 9. But, okay, so 9 over 1 times 36 over negative 2. Okay, so I end up with, I'm running out of space, 9 times negative 18. 36 divided by negative 2 is negative 18. My final answer is negative 162. Okay, and then the very last one, sorry, I know this is a very long video for your data. It just had a lot of explaining to do. At least you're still getting your money's worth for school fees. 4 to the power of 2011 times 4 to the negative 2012 times 4, and people freak out because I've got these very big exponents. Is it a problem? No. Use my law of exponents, same bases, keep the base, add the powers. So I'd have 2011 plus negative 2012 plus 1. Okay. Remember, this positive and the negative just creates a negative. So I have 4 to the power of 2011 minus 2012 is just negative 1, and negative 1 plus 1 is 0, plus 2 times 4 to the negative 2 is 2 times 1 over 16, because you take the 4 squared to the bottom, and this simply becomes 1 plus 1 over 8. If this is 8 over 8 plus 1 over 8, my answer is 9 over 8. And that is your final answer. Okay, long video. I'm going to stop here and we will let you know which numbers you have to do. But this is the exercise, and the more you do, the better you'll become. We will put up a clearer picture of it on your Instagram page. Have a good Thursday and have a good long weekend. Remember, we won't put up a video on Friday or Monday because it's Easter weekend and they're public holidays. Okay, bye.